Zahran is a professor with the computer science department. Oh, I am sorry, just allow me to start recording too. I was just almost missing that. Oh, actually, someone started that. Okay, so good. All right, so Dr. Mohamed Zahran is a professor with the computer science department at the Courant Institute of NYU. He received his Ph.D. in electrical and computer engineering from University of Maryland at College Park. His research interests span several aspects of computer architecture, such as architecture of heterogeneous systems, hardware-software interaction, and biological-inspired architectures. He served in many review panels in organizations such as DoE, NSF, and served as PC member in many premier conferences as a reviewer for many journals. He will serve as the general co-chair of the 49th International Symposium of Computer Architecture, which is going to be held in New York City in 2022. Dr. Zahran is an ACM Distinguished Speaker, a senior member of IEEE, senior member of ICM, and a member of Sigma Psi Scientific Honor Society. We are very happy to have you here. I'm super excited for your talk. So please start anytime.
All right, thank you so much for the introduction. Thank you so much for inviting me, and good afternoon, everybody. A lot of people are doing research these days, I mean, starting from 2015, where the word machine learning became a buzzword. So everybody were working on hardware support for AI. So we decided to go the other way around and discuss AI support for architectures. The whole idea we decided to go that way is that the hardware support for AI is the main reason AI became the buzzwords in the last few years. Remember that from the Dartmouth workshop that started, that was held in 1957, where the term artificial intelligence was coined, a lot of breakthrough happens and all of that stuff. But in all of these 70 years, AI was not the buzzwords until about 2015, where the hardware became strong enough to run these type of architecture. These types of software. And of course, when we say AI, we really these days mean machine learning. Okay, so a lot of work has been done in hardware support for AI, whether this is for training, as we see in many GPUs, and a lot of TPUs from Google. These are for training, the two main competitors for training. And then there are about 3 or 4 dozens of startups who are designing a lot of hardware for inference. Now, what about the other way around? When we say AI support for hardware, what do we mean by this? The only form of intelligence or any kind of optimization that has been used for hardware design earlier was in computer-aided design, in the CAD tools, and on the placement and routings and all of these interesting things. However, these type of things are kind of static. You are giving the problem, they give you a solution, and that's it. But what we are looking about is something that continually keeps learning and enhance the hardware. People may say that we had some attempts in hardware in the last 3 decades that we can call some kind of intelligence. Branch prediction, for example. Branch prediction is learning the history of branches in the program execution and starts, predicting the future, which is, we can assume it is kind of AI support for hardware in that regard. But we want to take this step further. How to make the hardware, the whole hardware, learn from executing programs and get better at executing different programs. And this is the key point. Learning from programs and use this learning to make different programs run more efficiently. In branch prediction, in cache replacement policies, you are learning only whatever is happening in that program. You don't really transfer the knowledge anywhere else. Can we do better? Let's see. everybody knows profiling. We have been using profiling in a lot of experiments, whether we are designing hardware or whether we are designing compilers or enhancing our software, where we are taking a program, we execute that program, and we get the output. And with the output, we get a lot of statistics, a lot of profiling data. Using this profiling data, we used to do one of two things depending on the kind of research or work we are doing. Either we'll use this to optimize the hardware, to reconfigure the hardware, and this is done by the hardware companies. They are using the benchmarks to try to make the newer generation of their hardware more efficient and so on. Or if you are designing compilers, for example, then you can use this profiling data for feedback-directed optimization, binary editing, code optimization, and so on. However, if you look at all of this thing, and there is a large number of papers about that, this literature here is very rich, that we are talking about the same program running on the same hardware. Now, we need to take this one step further. Can we take this to the next level? What do I mean by next level here? If you think about it, we have a program and we have a hardware. We can have the same program or different program, same hardware, different hardware. So we have 4 quadrants. What we have been doing so far in all the literature in the last several decades is same hardware, same program. You are trying to optimize that program to run on that hardware, or you are trying to optimize this hardware to be good on average on those type of benchmarks. And everybody had some very nice hard time working with the spec, CPU, starting from 1999 until 2011 and the ones that we got recently. And now we have parsec for the parallel and many of these things. However, we are still talking about same bunch of programs, the same hardware. Okay, now we want to look at what if we run a program on a hardware, we gather this information, profiling data, and we want to use this profiling data to make different program run on that same hardware. So we are transferring the knowledge from one program to another to get the best of the optimization. Do we really need this? Well, let's think about it. When you are designing a multi-core processor, general purpose, that chip will be good on average for everything, but it will not do its best on every program. This is one thing. People may argue, okay, we are in the era of application-specific chips, and that was the main point. If you have heard the Turing lecture by John Hennessy and David Patterson a few years ago, that we are in an age of application-specific chips like GPUs, for example, FPGAs and all of that stuff, which is true. But even these chips, a GPU, for example, is very good in running special types of software. But the word very good here means it is much better than multi-core. It doesn't mean it is the best thing the GPU can do. So basically, whether we are talking about application-specific chips or general-purpose chips, we want these chips to reach their full potential when they are running a program. The only way for something like this to happen is that we have to keep reconfiguring these chips whenever they run a program. So now we have a program running. Now, what is the best hardware for that program? And then there are some knobs that will be turning. Let's use the word knobs now, but it's just some kind of reconfiguration. Another program is coming, then we have a different reconfiguration and so on. The idea seems logical at the very beginning, but as you know, the devil is in the details. For instance, what do we mean by knobs? How many of them? How can we reconfigure all of these knobs? And doesn't this make the hardware more expensive? And then when we say a program starts running, a program that starts running does not have the same characteristics during its lifetime. When the program executes, it goes through phases. Some phases are repeated and all of that stuff. And there is actually a whole research group producing a lot of papers in the last, like in late 90s, early 21st century from US San Diego about program phase detection and all of that, stuff, how to detect a phase of a program and all of that stuff. So basically, we need to reconfigure the hardware for different phases of a program to get the best thing about it. Okay, fine. I'm putting a circle here around number 1 because this is what we have results for. Number 2 and 3 are still our future thing. So how do we know that something like this will work? Well, let's think a little bit. When you are executing a piece of software on a piece of hardware, we are looking for patterns. It's all about pattern. A piece of software that executes on a piece of hardware, you will find some memory access pattern, you will find some kinds of type of instructions are executing, how much they are using from the execution units, how much they are filling for the cache. There are patterns, a lot of patterns. Okay, if we can learn these patterns, you will find out that this pattern is independent from a program, which means that one phase from program A may have similar patterns than another phase of program B running on a different hardware. So it's all about the more patterns we get, the more we can more thoughtfully reconfigure the hardware. So the whole idea is to find these kind of patterns. So basically this is how it looks like. We have a hardware configuration and one phase from program B can get the same performance. This includes, when I say performance, I'm just using a generic word to mean really speed, power, and anything we want to measure. I mean, another program with a different phase, if it is executing on that hardware, it can also get the same performance and the same power. So this means that these two different programs with two different phases may have the same pattern in interacting with the hardware. And these two phases do not have to be the same number of instructions, by the way. So it doesn't really matter. The whole idea is to define what is a pattern, what is the best configuration for a pattern, and then how to detect patterns for an unseen program, and what to do if we find a program with a phase with no patterns that has been phased before. So there are a lot of open questions here, which is a good thing, because now each one of these open questions can be a good research thing by itself. So the ultimate goal is we need a machine that becomes more and more efficient, with the word efficient taken very globally depending on our measure of success, as it executes more program. We have three main challenges. Can we generalize that scheme to any program? Because when we started giving talks about this idea, people are saying, are you sure? Will this work for anything? Now that the word phases and all of that stuff was, very mature with a lot of papers about it, but that was during the sequential thing. Now we need phases for parallel code. Parallel code has more versatile pattern. Can we do that? The second challenge, the hardware may be expensive. If you want to have knobs, which means you want to turn off parts of the cache, you want to choose one branch predictor from different branch predictors, you want to throttle part of the pipeline, many things. We call all of these knobs. The more you add knobs, the more the hardware may become so sophisticated, and this is what you don't want, and especially that the reconfiguration will take time. Another thing, people may say, okay, the prediction of the best configuration is hard. Okay, we'll see. So what are the challenges here? The approaches that we have for every challenge. The first thing, we will need to study the different execution phases. We are taking several benchmarks parallel now. We are no longer working with sequential code. And we are looking at, we are defining our own definition for the word phase for a program. There are very few papers about phases of parallel program execution phases, but it is doable. And then we see, okay, is our hypothesis proven, which means we can find a phase from program A that has the same patterns with interacting with the hardwares, and another phase from program B, and so on. We did some extensive experiments here, and we are continuing this with different benchmarks. The hardware may be expensive, that is true. This is why we need as few knobs as possible that can have as higher effect as possible on the performance. For this, we decided to use two different paths. We, the hardware people, are looking at the hardware and trying to see, okay, for the different knobs, how expensive and all of that stuff. We have our own designs, and there are also a lot of papers, gazillions of papers on the digital libraries about many different knobs, but every knob is a paper by itself. Okay, and also the other path is we went to our friends in the data science department, and we told them, okay, these are the reconfiguration knobs. I want from you folks to tell us, to do a correlation analysis and tell us which knobs really have very high correlation, because two very high correlated knobs, one of them can be used only, because then in the other one, doesn't need to be used. This is one thing. Another thing, people may argue, okay, there are some knobs. Why don't you just leave these knobs by themselves? Leave the branch predictor to act by itself, leave the cache to turn on and off, the dark silicon stuff, if turning off some cores, turning off some parts of the cache. That is perfect, but you missed a small thing. Whenever you turn one knob, then you are affecting the performance of the whole machines, which means the other knobs also will be affected. The other knobs are built with the assumptions that the machine will stay the same, and I'm changing the branch predictor. Now, if you change something, then you are affecting this. So basically, we have a Pareto optimization problem. We need to optimize several points at the same time. And this is very challenging. The word challenging is not good for students. Interesting. Let's put it like this. This is an interesting thing that we need to look at. For the prediction, we are using also our friends in the department who are working in machine learning. And as you know now, most of the CS and ECE departments are calling themselves machine learning departments because they are buzzwords. So we can use those people and ask them, okay, what is the best kind of machine learning that we can use for this and for that? And we start explaining, because sometimes people just want to look very sophisticated and say, we are going to use some convolution neural network with whatever, and all what they really need is a linear regression. So basically, we need to know to define the problem quite well and see what kind of machine learning we'll be using. This is the big picture. Well, it's not big in font, but I wanted to put everything in the same slide. So the part on the left is offline. The part on the right is when we see an unknown program. So the part on the left, we run the several benchmarks. We detect the phases. We learn the best configuration. Since it's offline, we can, try different configuration and see what is the best one. And then we reconfigure, we continue execution, we see another phase and so on. So for these programs, we now know their phases. We know how they interact with the hardware. We know what is the best configuration with something like this. So now if we see an unknown program that has the same pattern, now we know what is the best configuration for that pattern. This is basically what happens now in the right part of it. It's very easy to explain these things. Now let's go for implementation. Then you will find several things here. Which knobs to use, why we are using these knobs, what is the best way to reconfigure these knobs. We want the hardware to be as simple as possible, given the reliability issues, the power issues, and performance, and all of that stuff. Okay, we need to detect phases with as few metrics as possible. We can use the performance counters, but actually there are those of you who have tried to use performance counters before, there are several restrictions, how many counters you can read at one point, and so on, and all of these things. So we need to have as few metrics as possible, but they have the best accuracy to detect a phase, where to store these metrics, and so on. How to determine a phase. We said before there are a lot of papers about program phase detection, but those were sequential programs. The parallel programs phase detection has very few papers, about 4 or 5. How to learn the best configuration, how expensive it is. Because if you have a large number of knobs, then basically the design space is very large to get the best configuration. So we need to do something about it. Finally, how to transfer now that knowledge. We need to store these things somewhere so that when an unknown program comes, we will be able to map these types of patterns and so on. So to put it in a different way, this is put in a flowchart way. The offline part on the left, which is exactly very similar to whatever we had on the right, on the previous slide. The unseen program will start executing. We will detect, once it starts executing, we will start getting measuring the matrix through the performance counters, and then we detect a phase change. Once we detect a phase change, we predict the next phase, because what we care about is the next phase. Now, that next phase, does it correspond to any pattern that we have seen before? If encountered earlier, then we will adjust the knobs to match that hardware that have been encountered in a previous program. Else, then we need to use the nearest neighbor thing to come as close as possible to a cluster of things. And then we will configure the hardware, and then we continue, and so on. After the end of this execution, we need to add this information to our database of patterns. Where here database is not really a database. It is just the weights of the neural network or whatever technique we use. So this means if we have a microscopic view on that part that was on the right in the previous slide, we have a phase, we detected there is a phase change. We have measured a matrix, some matrix from the performance counters, and now we need to predict the best configuration. Then we start executing, and then we see the performance. Based on this performance, we need to record, did we really get the best thing or not based on what we predicted before? If you look at this feedback thing, it just gives us a small glimpse about what will happen during the online thing, because this looks like reinforcement learning. So basically, we'll see the reward and penalty here. It means the performance, the power, and so on. So let's go one by one and show some results. The knobs, we need to have the knobs that have high impact on performance, which is not a very easy thing, because when we were discussing this I was giving a talk at AMD Research, and just for last level cache, they have more than 30 plus knobs there. So there are really large number of knobs. They don't really release all the names of the knobs because they don't want to release their designs, but they have literally for the whole processor more than hundreds of knobs. They have to easy to design these knobs. We need to be able to reconfigure things very easily. They have to be fast to reconfigure, because you don't want the reconfiguration time to kill you when it comes to performance. They want to be as independent as possible from each other. This is a correlation analysis, because two knobs that are very dependent on each other, we can just eliminate one of them for cost reasons. So let's start with a small experiment here. That was started with one of my students. We are trying only with one knob just to check whether this hypothesis of phases works or not. And we want to compare with something that has nothing to do with AI. So we are using one knob, turning off parts of the LLC. Few simple programs for training, and here Chris wrote 4 programs that are really very simple, something like matrix multiplication, linked list parsing, small sorting, and so on. Just 4 very simple things. Using these programs and finding their phases and learning the best configuration, we are using this information to see what will be the performance of parsec, which are quite sophisticated and more sophisticated parallel programs. So parsec for testing. This is what we get. All right, let me explain what is going on here. This is the size of the last level cache. So the blue bar is the full cache. We didn't turn off anything, so we have to compare against that. The EWSS is the extended working set size. That was some kinds of reconfiguring the caches published a while back by James Smith and his student in ISCA 2002, so we need to compare with somebody. And then we said, okay, we are going to use also neural networks that will learn from those simple programs, and then based on this, they will turn on and off parts of the cache. And also we will be using non-neural network, but something that has the capability of learning, which is Bloom filters. We are using Bloom filters that will learn those patterns and then detect what size will make the cache. The cache will move by 20%. So either 100% of the cache is on, or 80, or 60, or 40. We stopped at this, so we have only four configuration. What we saw here is the x-axis are the parsec programs. The blue is the full cache. And then after that, we will see what is the average cache size throughout the whole execution of parsec. So the lower, it means we are turning off more of the caches. So as you can see in all the learning stuff, the Bloom or NN, we are even lower than the EWSS in most of the benchmarks, which is good if we just look at this figure. But okay, how about the performance? Yeah, we are turning off a lot of part. I can keep the cache at 40%, but what did we suffer? All right, first, this is the miss rate, and the miss rate is almost the same. We didn't really lose, even sometimes the EWSS increases a little bit the miss rate, but on the others, we didn't suffer a lot. Look specifically for the red and orange, because these are our techniques using the Bloom filter. So we didn't lose anything. Okay, you may say, okay, this is a miss rate, but you have a hardware for reconfiguring and all of that stuff. This may take time. How about the performance, the overall performance of the system? This is the performance, the total execution time. And as you can see, we didn't suffer also any of these things, except just few, the ray trace and all of that stuff. But the ray trace and the phase sim, they are suffering a little bit, and this little bit is less than 10% for one reason. It's suffering from the neural network, not from the bloom, because the neural network really requires huge amount of data to learn for training. And we used only 4 simple programs just as a proof of concept. We want to show that 4 simple programs that have nothing to do with parsec can make more sophisticated programs like parsec run more efficiently. So basically, this is what we found here. Let's make it a little bit harder. 4 knobs. Turning on and off part of the LLCs that we have seen, turning on and off part of the L2. Our design has L2 private, which is very similar to Coffee Lake, Kappy Lake, and all these last half a dozens of lakes that Intel has generated in the last decade. We are turning on and off the prefetcher that is working on level 2 cache, and we are turning on and off parts of the BTB, level 2 BTB inside every core. We have reached this with the performance analysis that we ask some students to look at a lot of knobs, and we find those that have the highest impact. And we are using now parsec for both training and inference, but it's not like cheating. We divided parsec into two parts. One is used for training, the other is. And now we are using reinforcement learning. Things are becoming a little bit more sophisticated, that now with all these knobs, we may find patterns that have not been encountered before. So in that case, if we don't find a pattern that hasn't been found before, then we need to use some reinforcement learning to make it as close as possible with nearest neighbor of a pattern. And then we use the reward or the penalty to readjust the configuration, and we will save it afterwards. So this is one of the things, and we are trying to improve both the performance and the power now. All right, these are some power saving partial results for the power saving. Now, I wanted to put several of them in the same picture. Let's see. The baseline is when we don't configure anything. This is the black long bar that is there for all of them. We didn't do anything. The others are some small tweaks for the forecasting thing. One of them is we are learning, but we are not using the new programs to enhance our learning. So there is no continuous learning. The other one with continuous learning. The third, we are using a table to learn the Q factor. This is for the reinforcement learning. On the others, we are not using the table, but we are using a neuron. So we tried several things, and we will try to understand what is going on. Now, if you look at these graphs, the lower the better, because this is the power consumed. And as you can see, in almost all our cases, we are better when it comes to power saving. We saved about 15 to 20% on average from the power on most of the programs if we compare it to the baseline. Okay, this is encouraging, but it's by no means conclusive. So let's look a little bit more about this. Now, in the offline part that you have seen from the previous, from an earlier slide, we have been testing phases, detecting phases, and then trying several configurations until we find the best configuration, and we store this. We say, okay, these are the metrics that form the pattern, and this is the best configuration for that pattern. Now, during execution, we measure metrics. So this looks like patterns that we have seen before. This is the best configuration. This is not. Then we are using reinforcement learning and nearest neighbor. Fine. But the offline part, if we want to use these techniques in real life, and if you have really hundreds of knobs, then you will take forever actually to try different configurations to find the best configuration for a phase. Okay. Now, how can we test then different configurations without really reconfiguring the hardware and executing it? That is an interesting question, because, you know, we have one big problem that we try to solve. Our hypothesis And then once we go into the details, we have many other problems that we try to solve. And each one of these problems may be a good contribution by itself. To test the different configurations, one of the things is to do performance prediction for parallel programs. That is really a nightmare if you want my opinion. We have been trying to do this. Well, performance prediction was much easier for sequential code. It is much harder for parallel code, and it is a nightmare for accelerators. So let's see what is going on here. Testing different programs configuration. It means executing different configuration of the training phase and see what the performance is. But this is, as we said, with the large number of knobs in real life, it will take forever. So we need to predict the performance. Okay, now you want to predict the performance of a phase of a parallel program on a specific configuration. Fine. What is your input? What is your output? We need several metrics. Which metrics shall we use, to be able to predict the configuration? So we went again to the data science folks. Okay, and one of the hardest thing when you do hardware with the data science folks is that you have to explain hardware to them. This is much harder for us than doing the work ourselves. But this is how it is. I mean, yeah, they have heard about something called cache, but when you start talking about branch prediction or prefetcher or these things, or even worse, variability or reliability, and then we are in a different stage. Okay, so we made some, or they made some kind of performance prediction using these features. They are calling them features. We in hardware, we are calling them metrics, but basically these are the ones that they found after they analyzed hundreds of metrics, and they found that these are the best when it comes to prediction accuracy. And they tried several things here, starting from linear regression, and I asked them explicitly to try linear regression because sometimes things are much easier than they seem. Just in case, Gaussian process regression, decision tree, random forest, support vector regression, and k-nearest neighbor to predict the performance. And then we run it on the hardware to see really what is the mean absolute error for something like this. And these were the best, basically, in many different programs, parallel programs, the decision tree and the random forest, consistently, when we tried them on all the parsec thing. Which is basically, for some reason, they told me that these are the best in most of the predictions they are doing. And then I started really questioning why do we have the others? And I mean, they look like they are quite good in everything. I mean, but okay, so this is what we have, and we are using DTR or FRR, to predict the stuff in the offline part. This will make the offline phase much faster. Okay, and this actually, to some extent, gave us very encouraging results on the phase, the milestone, or the phase 1, which is different programs running on the same hardware with the knobs and all of that stuff. Still, of course, there are more rigorous experiments that we need to go beyond parsec and try different things. We need to include accelerators, which have been delaying for a while until I see what is going on in here. And shall we take the accelerator like a GPU or a TPU or an FPGA by itself, or shall I take the whole system as a whole, including the multi-core? In that case, we have to take also the metrics of the interconnect, PCI Express and VLink. They have their own knobs, so things are, will explode here. But we are working for this. After that, moving to milestone 2, which is the same program but different hardware, and then the most ambitious, which will signal the end of that whole project if it is successful or failure. Anyway, we'll learn something, which is different programs from different hardware. I know that I have 30 minutes only, and I know that I'm about to be done with my thing. So I will conclude that what we have learned so far is that we can learn a lot from the profiling data, not only for that program running on that hardware, but for different programs running on the same hardware, and hopefully we'll use it for different programs running on different hardwares. And also what we have learned is that coordinating these knobs will give you much better performance and efficiency than leaving these knobs by themselves as we have with the current processor architecture. Okay. With that, I think I'm ready to take the 10 minutes. We have 10 minutes. We are ending at 3:10, right? So now it's 3. So I'm waiting for the questions. Usually, if we don't get any questions, either it means things are crystal clear, or I'm a bad teacher, or you don't care about what you have. Let's see.
So we actually do have some questions, but thank you very much. So like audience here, we can actually.
Thank you so much.
So yes, so on the chat, I was receiving some questions, but I just waited for the talk plan. So I'm going to go over the questions.
Yeah, unfortunately, for some reason, I don't have access to the chat. This is why when I'm sharing the screen, I don't get the chat. I don't know why.
So now I'm gonna go ahead and ask the questions and pick some questions, ask some questions, and if you have extra time, I can ask one of my questions too, probably. So let me go back to Matthew Sharp. He's asking, do you have any difference in performance if you change between computer architectures? For example, if you go from an x86 to, let's say, RISC-V, for example. Different instruction set architectures.
Yes, actually, we are not using x86. Who is using x86 anymore? I mean, even the x86 Intel processors are really executing micro operations. But we are using the multi-2-sim simulator, and we configured it to be as close as possible to Kaby Lake. Why Kaby Lake? Because this is as close as possible to many of the things like AMD Threadripper and so on. And we tried different things, but the ratio is the same. We are getting very comparable results, even if we change the number of cores, the interconnections among cores, if I understood the question correctly, or the cache configuration, we are getting very similar results, which is very encouraging. This means the hypothesis is still holding.
Makes sense. So we have another question, which was kind of my question too, from Mohamed LTT. And so I guess the question is, do you imagine using this optimization as a part of compiler in the future? Let's say we have architecture and hardware system that supports this knob tuning. Is this something that can be done at the compiler level?
Yes, definitely. It can be done, and there have been some work done long time back at University of Virginia by Marie-Lou Sofa about continuous compilation. So basically, they compile, they run the program. At that time, it was sequential code, but that's fine. And then they gather some information, and then they recompile parts of the code with binary editing. So they are putting in the hardware part of the compiler to keep enhancing the code. And the reason for something like this is if you have a software on your cell phone, for example, and your battery is full, then this means you need to optimize the code for performance, getting the best performance of that code. Now, if the battery is low, you need to re-optimize the code for power, not for performance. If you are walking and you have something with low signals, then you need to re-optimize for the third time your code for communication. You cannot optimize for all, so they put it there. But the problem will be easier if you want to use a compiler offline, which has been done also by feedback optimization. Anyway, so basically we can use this optimization, but people have been using it so far for the same program. Now we need to take it for a different program. We need to get this profiling data to enhance the optimization of a different program by the compiler. And we believe it is very doable, and we believe it's even easier than doing it on the hardware. A lot of work on the binary optimization has been done also by Kim Hazelwood. At that time, she was at UVA. Now she's at Facebook.
Interesting. We have another question too. So I assume that most of the simulations that we talked about, so I'm paraphrasing what Mohamed Reza Mohammadi mentioned. So he has a question. Paraphrasing that, I assume that most of the simulations that we talked about was running one benchmark on the general purpose processor that we have. So he is asking, do you think that we can support running multiple programs, like when we're working with computer, multiple applications, or running at the same time for different phases, and we tune the knobs at the same time in different cases?
Yes, I was expecting this question actually. It will be a nightmare. It will work, of course, but it will work we need to change what we are doing now, because basically this means that you are not really running on that processor, you are running on a reduced version of that processor, because the other part is taken by different programs. So basically you have to find what is the hardware that you are using, and then you start applying what we are saying on that part. Then when the operating system and its interaction with the different processes decided to give you a little bit more or a little bit less than the hardware has changed. In that case, I highly suggest then that we have to involve people from the operating systems, because then the operating system folks, when they schedule the processes on the cores with the different knobs, they have to take this into account. So I believe that part of the solution, and these are still my guess, we haven't tackled this problem yet, it has to come from systems, from the operating system.
Yeah, absolutely makes sense. I actually have a question myself, so we have a little more time, and I think Mohamed has a follow-up question. So I go with my question, and then we can go back if we have some extra time. So you mentioned something about the AMD, although they don't provide the information, obviously, because of the intellectual property and everything. And you mentioned that they have many knobs around on the architecture. So do you think that they actually have those knobs as tunable knobs, or they can be potentially looked at knobs? Is the hardware there now, or they have to add something to the hardware to be able to tune the knobs?
Okay, well, what I will answer will be my guess, of course, because they don't provide this. So it is not, most of them are not yet reconfigurable, but they are there for future upgrade. This is one thing. And for the fabrication, because for the same architecture, you want to use this for different market segments. It's like when you have like Kaby Lake, for example, or Ryzen from AMD, and then you want to put them like the i3, i5, i7, and so on. But whether they are reconfiguring all of them, I am not sure yet, because from the type of interest we saw when we told them what we are working on, it seems they are not yet in that. Maybe they are reconfiguring very few of them, but not those hundreds that they are, because that will be still, very expensive.
I understand. Yeah, that makes sense. That makes sense. So we are at 3.9. If you have time, I can ask the follow-up question that Mohamed asked about the compiler.
Sure.
So he is saying that, do you think that we can encode programs such that they're kind of fixed, and the training process is on the compiler side, and the hardware is always being run passively? So I kind of think this is what you were already mentioning. So if it's not in the compiler, the training is happening, the hardware, the knobs are being tuned.
So you mean, sorry, I missed this part. So you want the hardware to be fixed, not reconfigurable, and you want to change the binary. Is that what I...
Maybe Mohamed, you can go ahead and provide some more details, because the question, I'm a little bit confused too.
So what I mean actually is, what if we train the compiler to understand the hardware? So I guess.
Oh, okay. Well, the compiler already understands the hardware. The back end of the compiler understands the hardware, and the compiler will try to generate the best machine code for that specific hardware. But the idea is, when we get the profiling data from a different program, can we use it to make the compiler generate more efficient instruction for that same hardware? I believe it can be done. I mean, with the hardware being fixed, it can be done. I'm not aware of anybody who has done this yet, but I highly believe that it can be done, yes.
Thank you so much. So we are right on time. I appreciate you accepting giving us a talk, and it was a great talk. We can have follow-up questions possibly later, but I am sure that the audience loved the talk as well. Again, we appreciate you being here, so we can maybe have another round of applause for answering the questions. Thank you so much.
Thank you so much, and I will share with you the slides as we said before the talk then. And I will be more open to any more questions by email or so.
I appreciate it. Thank you so much.
Thank you so much. Yeah. Have a great weekend.